we had the chance to talk about OpenXLA, and Forbes picked it up as one of the top 5 things to watch for at Davos. And as a result of it, there's a couple of other media outlets that have also reached out who want to kind of highlight some of the great projects that this community is working on. So hopefully this is only the beginning.
Great. Thank you, Aditi, for representing OpenXLA, and really glad to see the interest from media. Okay, with that, let's move to the next topic. James is going to talk about the upcoming DevLab. James?
Yes, thank you. And thank you, Aditi. We're super excited to have you on the team presenting at Davos, as your first OpenXLA experience is no easy task, to say the least. So thank you for that. Switching gears slightly, last year, one of our biggest pieces of feedback was providing more tutorials and hands-on examples for OpenXLA components and their respective user flows. We think one of the best ways to provide that is through a hands-on in-person session with XLA, StableHLO, and PJRT engineers. And that's where this OpenXLA DevLab event we're presenting today comes in. So this event is going to be specifically focused on our AI hardware and compiler software infrastructure developers. That includes existing OpenXLA contributors, of course, but also new teams and developers that are interested in getting involved. With this, what we're really aiming to provide is deeper education on the core contribution flows for OpenXLA. For example, integrating your hardware backend or compiler into PJRT and StableHLO. Additionally, we want to offer ample time for you to collaborate directly with a dedicated XLA engineer on a use case specific problem or project that you're working on. So the agenda, as I kind of alluded to, is first we're going to have a very brief keynote presentation that discusses some of the biggest product milestones since the last summit and a recap of our 2024 plans. That'll be around 30 minutes in length. That will be followed by tutorial sessions for those key contribution flows I mentioned, PJRT plugin, developing a compiler pass, etc. These will be more one-to-many type walkthroughs that deep dive on those specific projects, and they will last about an hour. But the bulk of the agenda, about 3 hours, will be lab sessions. And these lab sessions will provide the opportunity to deep dive on a specific OpenXLA related project that you've been working on and work through that with a XLA, JAX, StableHLO, or PJRT engineer. That project could be a contribution in process, an RFC, a design, a set of bugs, etc. So these sessions, just as a heads up, will require a little bit of homework on the end of you guys and the attendees. And that's so that we can really, prepare our engineers and ensure that they're making the most of your time. And in turn, they'll do the necessary preparation as well. So this event is planned for the upcoming April 25th. It's going to be in Sunnyvale, and we're going to be sending out an invite later this week at the latest, early next week, with all of the details around the venue and the agenda and so on. Aditi will actually be sending that out and will be a primary point of contact for this. So if you have any feedback or requests, feel free to email her, and you can CC myself and Sace from the product side and Ginny from the technical program side. And yeah, I guess I'll stop there for questions, and we're super excited about seeing you there.
Thank you, James. If there are any questions or a follow-up, yep, go ahead, Rahul.
Yeah, I had one question about this DevLab. Is this in person or virtual or both?
It's in person, and we're going to provide the ability to call in remotely. However, we really do encourage in-person attendance, just given the nature of these sessions. And it's likely that remote attendees will, have obviously lesser involvement in the actual activities. But we will be providing, the ability to attend virtually. We do strongly recommend in-person attendance.
Okay, thanks.
Okay, thank you so much, James. Really looking forward to the event. Yes, please send us any feedback that you may have. Aditi's contact us here, so please reach out if you have any further questions. Okay, with that, let's move to the next topic. We'll go into technical updates. So the first one is moving TSL into XLA RFC. David?
Yeah, hi everyone. I'm David Dunleavy, and I think a month or 2 months ago, I presented about an RFC about moving TSL into XLA, and no comments on the RFCs, so as planned moving forward. And this is really just for anyone who's using XLA code directly in a different project and may need to do pin updates. So I'm going to hopefully try to make that make this as smooth as possible, but if anything goes wrong, just leave a comment on the RFC. So over the next month, targets will move from the TSL project to XLA subdirectory within XLA called TSL. And so if you use any of these headers directly, there's going to be replacements needed on pin update. What I'm going to try to do is do the changes from least disruptive to most disruptive. So hopefully if you are doing a pin update, you can ignore it until the very end and it won't affect you. And then right at the end, it'll just be one big find and replace to fix everything. So besides renaming though, there should be no other breakages, not changing any functionality besides that. And just, yeah, please let me know if there intermediate changes are causing any problems so I can try to help out, because it really should not be too disruptive, but just want to make sure that if this is affecting anyone, they know who to talk to figure it out. So should be done by the end of February. And so the easiest possible pin update, it should hopefully be easy until then, and then there will be just one big pin update you'd have to do to update every reference, and hopefully everything goes smoothly. So if this is causing any problems for you, please reach out. But that's it.
Thank you, David. Any comments or questions for David is here? Okay, all right. If any further questions, please reach out to David. Thank you. Let's move on to the next topic. So we have PyTorch XLA performance update by Frederick from Google.
Hi everyone, I'm Frederick. I'm in the PyTorch XLA in the XLA GPU team. I'm focusing on PyTorch XLA, and this is joint work together with the PyTorch XLA team, which Milad is leading, who's also on the call. So what we did is, our goal is to make OpenXLA great together with PyTorch. So why do we care about PyTorch in this context? PyTorch is obviously the most popular ML framework today, at least outside of Google. And we have to deliver great performance in PyTorch and also great usability for people to use it. That is to say, most people will likely give it a try if it's easy to try it out. But if it's hard to try out OpenXLA from PyTorch, then it is less likely for people to try it out, and we want to make it as easy as possible, so that people try it out, see that it is giving them great performance, and then move forward. So it's really about promoting OpenXLA in the PyTorch ecosystem. On the other hand, what can OpenXLA bring to PyTorch? Why should the normal PyTorch user care about OpenXLA? And the long-term goal is to give hardware optionality, so that you can choose between all the different backends that OpenXLA supports. That includes TPUs, GPUs, CPUs, and all the others listed on the slide. The other thing we want to achieve is framework optionality. We want to have one GPU compiler for both PyTorch and JAX, and also for TensorFlow. That means that we don't have to work on many different compilers if we support multiple frameworks as we do. And then also what are aspects in which OpenXLA is better today than PyTorch Inductor, which is the compiler that is built into the PyTorch ecosystem. So we did a little bit of an analysis and benchmarking, and turns out the early numbers suggest that OpenXLA delivers better code gen on GPUs. So the kernels are faster on average. We have potential for performance at scale. That is things like SPMD and PartIR, where you do large-scale training on multiple hosts or multiple devices. That is something that is not supported by the PyTorch Inductor compiler. PyTorch obviously supports it, but not through a compiler. And we expect to get much better performance at scale if we leverage these XLA features from within PyTorch. Another thing that's worth noting is faster compile times. Inductor does a lot of compilation in Python and then invokes all sorts of compilers, and that takes time. So it's a relatively slow compiler. And XLA uses many of the same technologies. It uses Triton as well. It uses cuDNN and other NVIDIA libraries. But it does that from it's all implemented in C++, and it does not generate code and invoke compilers on the side. So in our experience, it's about 2 times faster on TorchBench. So that's significant. It's significantly faster, and it's still a goal to make XLA compilation time even faster. So we see that as an advantage of OpenXLA over PyTorch Inductor. Next slide. So where are we today? This is our analysis and benchmarking of PyTorch XLA in the context of GPUs and what we've done over the last couple of months. From our side, this work started in November of last year, but Milad's team has been working on this for a lot longer. So what we focused on is TorchBench, which is a popular benchmarking suite for PyTorch. And so that's just a go-to benchmarking suite for PyTorch. What's been challenging is that it's hard to match precision and the configuration of these benchmarks. So it happens relatively easily that one runs in a different precision than the other, which obviously has huge performance implications. And then you end up with a non-fair comparison between XLA, OpenXLA, and Inductor. So it's been quite challenging to match precisions and configs of these benchmarks, but we're making continuous progress. We've completed that for inference. We are fairly confident in the numbers for inference and see that we'll see the numbers, how OpenXLA compares against Inductor. We're not confident yet for training, but that is work in progress. We're drilling into it and are working on a fair comparison between Inductor and OpenXLA for training workloads as well. So accomplishments today, and the first one is mostly it's awesome. So on Milad's team, pass rate increased from 52% to 94%, and that is compared to Inductor. So not all benchmarks in TorchBench are passing with Inductor, but at this point, most of those that are passing with Inductor also pass with XLA or with OpenXLA. We unified benchmarking scripts, so all this benchmarking setup is upstream, so you can do that yourself and reproduce those numbers. That's been unified, and we have nightly benchmarking runs that already caught regressions. We have many metrics that aid debugging, that is to surface the most performance critical things that can happen, things like graph breaks, individual kernel times, etc. And at this point, 80 out of the 85 models are passing with OpenXLA, but at the point at which the charts on the following slides were generated, it was only at 64 out of the 82 models. So keep that in mind when we look at the numbers. Next slide. This is Milad. Do you want to talk about this slide?
Sure, happy to. Yeah, so we are building out a. First of all, did you guys hear me well? Just to check the sound. Right. Yeah. We are internally looking at building a comprehensive dashboard that can serve multiple goals, or let's call it multiple stakeholders, people who have engineering background, working on, debugging a lot of the different challenging problems on these models, all the way up to people who are looking at a large benchmark suite like Torchbench from a product standpoint, from leading different types of technical initiatives. We have a kind of a summary dashboard that goes through the high-level details of how successful we are on a frequent basis, let's say daily, weekly, or something along those lines. Are we making progress to run all of these models at different hardware backends, like say NVIDIA L4, A100, H100, so on and so forth, and other backends, and also how is the performance, compile time performance, runtime performance, and a large collection of other metrics. But then there's also the angle of, and how are we comparing in terms of performance, speed up between different configurations. And there's also, based on this high-level information, you may take away certain, business decisions, or you may want to add, to dig deeper and understand better what's going on with each one of these individual models. If there's a significant regression or improvement, what was the source of it? What model led to that improvement? So what we have is a drill-down dashboard that allows you to actually jump into the model-level specifics and download logs and profiles associated with each model, and look at every single line of code that matters to you, and try to compare and contrast. That we believe will significantly expedite the user experience and developer experience to resolve their issues. Currently, this automation stack is something that's internal, and what we intend to do is to make it public after a while of doing a beta testing internally at Google. So this is something that I would encourage folks to look out for in the future. Back to Frederick.
Thank you. Next slide. So the PyTorch XLA has focused mostly on TPUs in the past, and the GPU support is relatively new. So there are still a couple of performance problems in the stack. So we don't have great performance out of the box as of now, but we're working on it, and we identified the critical performance gaps, and we have a plan to improve both the bridge, that is the integration into PyTorch, as well as OpenXLA itself, so that we do get state-of-the-art performance on PyTorch workloads. To understand the benchmarking results as of today, I want to explain a little bit about how the integration works, and some of the performance problems that we run into. You start with the PyTorch model at the very top, and then PyTorch has a mechanism called Dynamo that is basically a tracing JIT. So when you call a function, it doesn't execute the function, but it traces and analyzes the functions, and builds a graph, kind of like an IR out of it. And that graph is then passed to a compiler. So if you use PyTorch Inductor as your compiler, it's been passed to Inductor, and Inductor does the compilation for you, and then runs and executes those compiled graph models. The same thing happens on the PyTorch XLA side. Just in this case, the conversion is to stable HLO, and then that is being passed to XLA, where it's being compiled and then run. So today, most of the performance issues are in the PyTorch XLA bridge, and I want to dive into two of those specifically. just so we understand the huge performance implications of those. So the first one is graph breaks, and that is a big performance issue today. The ideal case is where we have a full graph, and that applies to half of the 64 models that we analyzed when these numbers came in. And that is the case where Inductor and XLA see the entire model and they optimize it holistically. So they get a view at the entire model and they can optimize across the entire model. PyTorch itself encourages this with the full graph mode. So this is as the desired way to go through the compiler. So both PyTorch Inductor and XLA, they run into this problem. But we do run into this problem a little more often than Inductor does today, but working on improving that. The less ideal cases where we have graph breaks, that also applies to about half the models that we looked at. And in this case, the compiler only sees a fraction of the model, which does hinder it to optimize across those boundaries. So the PyTorch XLA bridge today introduces some avoidable graph breaks that we're working on and expect those to disappear eventually. That's just work that has to be put into the bridge, and then we get rid of those graph breaks. There's also some graph breaks that are inevitable, and that includes side effects or dynamism. Side effects, if you put a print line statement in your PyTorch program, there's no way to get rid of that. You can't put that into a graph, so you have to keep it and break the graph accordingly. If we go to the next slide, we have a little bit of a visualization of how this looks. So there's just an example graph at the bottom, and in this case, non-zero is not yet supported. So the compiler is forced to introduce a graph break, and then you end up with 3 different subgraphs, and the compiler can't optimize across those. Next slide. And this is the better case where there's no graph break in it, and then the compiler can optimize the entire model. Next slide. The second problem that is sometimes related is there are some optimizations that are operations that are unsuitable for compilation, for example, because they're too dynamic. It can also be that they're simply not implemented yet, which is the case for non-zero, which needs bound dynamism in this case. That's a detail. So for all those cases, we need an escape hatch. We have to have a solution for how to deal with those, and that escape hatch is fallbacks. PyTorch Inductor uses GPU fallbacks, of which PyTorch has quite a lot. So instead of compiling these specific operations, it just issues a call to a GPU kernel that already exists. They're reasonably performant, but they obviously don't support things like Fusion. PyTorch XLA, on the other hand, uses CPU implementations. There's good reasons why this is the case today, and it's not super trivial to change that. But obviously, that has huge performance implications if you run models on a GPU. For example, there's DLRM as a model where we would expect a 400 times improvement if we had GPU fallbacks. There's an in-flight proposal, so also this issue is being worked on. But with those two things, we can maybe look at the first slide with benchmarking numbers and see where we are today performance-wise. Next slide. Yeah. So this is a summary of the speedups for PyTorch XLA over Inductor. And this is geomean speedups across all the models in Torch Bench that compile in this mode. If you look at all the models, PyTorch XLA has a 0.55 speed up over Inductor, which means your performance is about half as, it runs about half as fast as Inductor, which means Inductor is better. But then if you look at the reasons why that is the case, some of the models are drastic outliers and drag this down significantly. So if you look at models that do not have any graph breaks, and that can be achieved by implementing the missing operations and having GPU fallbacks in the right places, then you already see a 0.9 geomean speed up across Torch Bench. That is still slightly slower, but is a lot closer than inductor already. Another thing we observed is when you measure the device on device runtime, we're actually already ahead of inductor, and that is without putting in any Torch Bench specific optimizations. So XLA is not tuned on Torch Bench at all, and for inductor you can expect that it is tuned on Torch Bench to some extent. So even with that, we already have kernels that perform that give us a 1.07 speed up over inductor, which is I found quite impressive. What we have to do to get from the full graph breaks to the expected without runtime overhead is we have to find and eliminate the runtime overhead that we currently have. That is some scheduling issue in the bridge that we do not yet fully understand, but that can surely be fixed, and then we are at a 1.07 speed up with rather little investment. Another thing we found is code gen issues in XLA. That is specifically around softmax fusions and flash attention. And if we improve those two things in XLA, and that we can expect by maybe the end of the quarter or slightly later, and then we get a 10% improvement over inductor. And that is just the beginning, because we're still looking at workloads, trying to improve things in XLA. So at some point, we will have larger speedups, hopefully. Next slide. So what do we have to do to get there? Famous North Star slide. The first thing is aspect is usability. We want to make it as easy as changing the backend for Torch Dynamo from inductor to XLA, and nothing else has to be changed in the PyTorch model. To get there is quite a bit of work, but we expect that to happen this year. The other thing we have to do is performance at scale. We need XLA needs GPU fallback kernels, which is being worked on. We need fewer graph breaks in the bridge. It's also being worked on. We need code gen improvements in XLA over inductor. That is what we work on. And then we also want to expose SPMD capabilities, where we expect huge gains over PyTorch inductor, because they do not implement that at all to date. Yeah, and that is the update about PyTorch. So in summary, we don't look too great today, but we have a very concrete plan how we can deliver greater performance than inductor and the same degree of usability. And I'm very optimistic and excited about 2024. And then everything is great. That's it.
Great, thank you, Frederick. I wonder if folks have questions, comments. Go ahead, Tejas.
Thanks, Frederick, for going through this, sharing these numbers. For the inference, have you attempted the multi-GPU or multi-node, or these are all single node numbers?
This is all single node at this point. Yeah, maybe you can elaborate.
So I can add some more to what Frederick mentioned. So when you look at Torch Bench is a single device type of workload overall. I mean, you can unpack some of the models in Torch Bench and run them on a larger data set and multiple devices, but the default setup is for single device for the most part. Having said that, we have benchmarked kind of some of the top line models in the industry, including Llama and Llama 2, on multiple GPUs for inference applications and also for training. And we have been able to obtain some promising results.
Yeah, thanks for sharing that.
Of course. So so there is a bit of a sort of like, how do we get to do that? Like, what kind of API do we use? I mean, there is a collection of different libraries out there in the public. We are supporting we do support SPMD, on the PyTorch XLA stack, and we are expanding that level of support. However, there are other libraries that give us the ability to have distributed APIs and collectives to run such applications on GPU. And we do support those collective APIs actively as well. Happy to go into the details if there was more questions.
No, that thank you for that explanation. Yeah.
Thank you, Milad. Any other comments or questions, folks? Okay, thank you very much, Frederick and Milad, for this presentation. Let's move on to the next topic. So we'll move to governance updates, and Jacques is going to walk us through some of the updates. Jacques, take it away.
Hi. Yes. Sorry about the delay there. I want to give a little bit of a summary since what happened last time. We discussed about rolling out of some of the new maintainers, and you're sort of like the list of folks, and we'll be expanding it as more folks join the project and lead more of the efforts. So we're announcing like two different sets of maintainers today. One on the XLA side. I'll go briefly over the names and sort of like some of the main areas where you'll probably see many of these folks being involved. So we have Andy Davis on horizontal scanning and the general support. David Dunleavy, who I think folks have seen earlier in this meeting on a lot of like the infrastructure work and benchmarking and the like. Eugene, who I think folks have seen in a lot of the runtime discussions, as well as some of the work on GPU side. George Karpenkov, obviously somebody more on XLA GPU side, and one of the leads there. Rahul Joshi, also working on horizontal scaling with particular focus on GPU. And in addition to the XLA maintainers announced, we're also announcing some new stable HLO maintainers. We have Kevin Gleason, who I think folks have seen on many of the RFCs over the years. And then Farid, who we met earlier in this meeting, who has just joined the team and is helping to set a direction and the vision more for the stable HLO direction. As part of this process, we are also, always trying to improve the process and ensure things are actually working well at the practical level, and serving the needs of the project as a larger in the larger sense. So with that in mind, we've been looking at how can we streamline the governance even more? How can we make it so that governance aids the project and in the goals that it needs to achieve, while not incurring too much overhead. And so we're in the process of discussing ways to streamline the governance process. And we'll probably discuss that in the next community meeting, or perhaps the one after that. Thank you. And next slide.
Okay, thank you, and want to congratulate all the excellent new maintainers called out here. Let's move on.
Yeah. So I want to give a little update about Erie in the project as well. So as folks may have seen from the mailing list discussion, Erie is moving out of the OpenXLA project. This is something where it's the process, as mentioned. There's been some discussions with the community in terms of like needs. So there's been a bi-weekly meeting where discussions in terms of like what is needed. Things related to like being able to submit your own CLs, CI, all of the how can we find a good neutral space for this, whether a project or a foundation, et cetera. And so this is one where we have the bi-weekly. There's the bi-weekly meeting on this, and requirements are being collected from our community's members, and we're trying to address them and find the best spot and make the move as simple as possible. Thanks. Next slide. And I'll hand over to Kevin.
Yes, thank you. So yeah, just to cover a few of the active RFCs that are open on the various repositories. I want to start with one that isn't listed here. In the December community meeting, we heard a proposal from NVIDIA for a new op called Collective Broadcast to enable better distributed training. This RFC was approved, and that's why we took it off this slide. But the update is Now the end-to-end support has been implemented and is in review, so that was super exciting to see. It's on the XLA repo currently as a pull request if you want to take a look at it or leave any feedback. Next is the Dynamism RFC, which was feedback was addressed and this was approved. Implementation is underway. This includes a few quality of life improvements for frameworks that are generating stable HLO programs with dynamic batch dimensions. Then the extensibility RFC is something that I'm currently pressing on, wrapping up. Most of the open feedback has been addressed. There's a few things that are still open that I'm working with the people who left comments to address the feedback, targeting end of February to introduce the stable HLO composite op for those who are interested in it. The transformations RFC was a recent posting done in collaboration with a few developers from ByteDance. We hit similar requirements at the same time, so decided to push through with an RFC together. Namely, this is asking to move CHLO decompositions to generate stable HLO, as well as adding some stable HLO canonicalizers. And this has had generally positive feedback, and some of these transformations have already been implemented, which was great to see. For hybrid quantization, there were no major updates from this. The team that's driving this hasn't had the bandwidth, but noted that it's still a priority. So we will likely hear some more feedback in the coming month. I would encourage anyone interested in quantization to partake in that discussion on the pull request linked there. And then the final row is compatibility. We're looking into extended compatibility for on-device use cases. The team driving this proposal is currently trying to find the more precise number for what the compatibility window should be. They're working with some app developers to find out how frequently models are updated in deployed apps and what the saturation rates are. And then once we have some data on this, we'll be able to form a more precise number, and we'll certainly share that in an update on the RFC posting. And then just lastly, for all of these, I wanted to note that most of these discussions started on GitHub issues or Discord or the OpenXLA discuss group. So I'd encourage anyone looking for RFC support to reach out in any of these forums. Thanks.
Thank you, Kevin. Let's move now to RFC process. Back to Jock.
Yeah, I mean, perhaps just a quick summary. So in the December meeting, we discussed setting up an RFC process for the project to use. And so this is one where there is a PR on the community forum showing the RFC process that we intend folks to follow. There's not been too much feedback on that, and so that will probably be submitting that one soon. And so then that will establish sort of a more formal RFC process for the project. And I think we should be probably land it this week or next week. But if any folks still have any comments, please go look at the PR on the community repo and feel free to leave any feedback. Thank you.
Great, thank you, Jock. All right, so that that was the last topic for our meeting today. I want to thank all the presenters for going through their topics, and if there are any questions or comments on anything, please feel free to reach out to the contacts that were listed, and let's continue to have this conversation on OpenXLA Discuss. Thank you, folks, for joining, and we will see you again next month. All right, goodbye.